All right, so in this exercise, we're going to talk about multilinear functions and figure out what the derivative of a multilinear function is. So just as a sort of a warning off the bat, this is a little messy, and I didn't take a lot of time into making this proof look as nice as possible. I was more of the opinion of, let me just get everything that's you need in order to make this proof, and then I'll just present it all, and it might not look super neat, but you can put together a neat proof from what I'm going to present. So, and I guess that sort of goes along with what I do in a lot of these videos, where my sort of mindset is not everything that I say is necessary, but the things that I say are sufficient for a proof. Okay, so let's see here. If we just have a bunch of Euclidean spaces, you can just consider these spaces to be like Rn, or yeah, just various multi-dimensional real spaces. It doesn't really matter. But a function f that goes from E1 through Ek into Rp is called multilinear if, well, basically if someone said that something is multilinear, you would sort of assume that means, well, it's the functions probably needs to be linear in each individual set in the direct product of its domain. I mean, that's exactly what this is saying. It's for every single... So basically, if you take this function, f, and you fix all of the space, if you fix the entry for all of the spaces in the direct product of the domain except one, and you let it vary in that one particular set, then it's linear. And that's basically exactly what this is saying. And so this is sort of a generalization of linear and bilinear to multiple direct products. So basically, what we know is we know for linear, and we proved in this section that for bilinear functions, the limit of the norm of f over the limit as h goes to 0 of f of h over the norm of h is 0 for the linear and the bilinear case. And what we're proving here in A is that that doesn't quite, you might think maybe it generalizes of like, oh, maybe norm of f of h over the norm of h equals 0 in the limit. And that's not quite true. Well, I guess that is that is a consequence of this, but something more specific is true, is that if you only let two of the particular indices vary in the numerator, then you still get 0. So basically in the numerator here, we've got f of a1 through ak, but you take two of those coordinates and you replace them with hi and hj. And this limit will be 0. And so basically we know that if you have this limit for bilinear functions, then this limit is true. And that's by exercise 2-12a from this section. So basically what we want to do in proving part A of this exercise is we want to use that. And it ends up being pretty straightforward. So it's going to be the limit as h goes to 0. I'll put the 1 over h out front to make it a little bit easier to write. F of a1, got the hi somewhere in there, and then we've got the hj somewhere else. Now, basically all that we need to do here is, so we've got this vector h in the denominator, and so this is going to consist of coordinates, let's see here, h. It's going to be h1 through hk, where each hi is an element of ei. And so, That's a little interesting. Actually, give me a second here. I want to see if this actually works the way that I think it should. Right. Bilinear functions. Okay, so bilinear, okay, so the domains are, for bilinear, the domains are Rn and Rm. Okay, so that's fine. So I guess the argument that I'm going to give only applies when the Euclidean spaces are Rn and Rm, but I assume that's fine because we really need to use 2-12a here. Or you know what? I'm sure that 2-12a generalizes to if instead of Rn cross Rm here, if you have E1 and E1 cross E2, where E1 and E2 are Euclidean spaces. I'm sure it generalizes like that. So we'll just assume that all those details have been taken care of. So we won't really worry about that. No. Tablet mode. Thank you. All right. So we'll assume that that's not an issue. Basically, I'm thinking of the EIs as RNs. Technically, the EIs can be more general than that, but whatever. Okay, so anyways, the point is 1 over the norm of H. Well, if you think about how you actually take the norm of a vector in Rn, basically here's what I'm going to do. It's going to be 1 over the norm of Hi and Hj. So we're singling out Hi and Hj. So basically what we're essentially doing here is we're taking that vector h and we're setting hk to be 0 if k is not equal to I and not equal to j. And what this does is it brings the vector closer to the origin, so it's obviously going to reduce the size of the vector. And that's going to increase 1 over the size of the vector. And so this inequality holds. And so we'll have, I'll just write f of dot here. And by dot, I mean a1 all the way up to hi. It's a1 through ak, but then with hi and hj thrown in there. It's exactly what we have in the previous, on the left-hand side of the inequality. I just don't want to write it again. But yeah, so we've got this limit. But now this f of hi and hj, this is a function of hi and hj. And if you consider it as a function of hi and hj, then it is a bilinear function because all of the ak's are fixed. And so we can apply exercise 2-12a to conclude that this limit is 0, because it's just the norm of a bilinear. It's exactly this sort of limit that we considered previously. And of course, this limit as h goes to 0 here in this case, that's the same as the limit as the vector hi comma hj goes to 0. Okay, so that's pretty straightforward. I left out a couple details that you about like the Euclidean space thing and stuff, and you can go back and fill in the details if you want, but I think this is sufficient. I think anyone reading this will sort of understand that that's all fine. All right, so now B is prove this formula for the derivative. So let's see, how are we going to do this? First of all, in part A, notice that the AKs can be anything. And that's useful because here we're going to use some of them to be 0 in part of this. And so basically part B, we need to show that this sum from I equals 1 to k of f of blah, 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 we need to prove that that sum satisfies the condition that the derivative needs to satisfy. Namely that the limit as h goes to 0 of 1 over h of the norm of blah, 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 blah. So before going into that, So make this proof clearer. For k equals 3, we have... Okay, so I just basically want to write out the case for k equals 3, because that will make this a little bit... it'll make it a little clearer what's happening. So here we're going to do f of a plus b plus, or minus f of a minus the sum from I equals 1 to k of f of a1 through... What I'm going to do is I'm going to do dot, and then... Let's see, how do I do this actually? No, here's what we're going to do. A plus h, a, f, and then h, I, dot. Okay, so this function f, this is f of a1, comma, dot, 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 comma, ai minus 1, comma, hi, comma, ai plus 1, comma, dot, 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 comma, ak. I didn't want to write all those a's in there, so I just replaced them with dots. And I'm telling you what those dots are supposed to mean. If you were writing this up for someone, you would have to explicitly write those. But because I'm explaining this to you via words, I can just say that. And that's it. That saves me time for writing. Okay, so this is the type of thing that's going to go in the numerator of the formula that we're going to look at for evaluating the derivative. So what is this equal to? So what we need to do is first we need to take f of a plus h, and then we use the fact that f is multilinear to expand this. And basically, what you need to do is you need to expand each coordinate individually. So what this f of a plus h, of course the arrow thingies over them means that they're vectors. So this is f of a1 plus a1 plus h1, comma, a2 plus h2, comma, a3 plus h3. So the first thing you need to do is you need to split up the first coordinate. So you get f of a1, comma, a2 plus h2, comma, a3 plus h3, plus f of h1, comma, a2 plus h2, comma, a3 plus h3. And then, so you've split that up into two on the first coordinates, then you need to split up each of those based on the second coordinate, and then you need to split up each of those based on the third coordinate. And so what you should see is that if you expand that out, you'll get f of a1, a2, a3, and normally you wouldn't write all this out, but I want to make sure it's really clear what's happening here. a1, a2, h3, and of course you can skip ahead if you don't want to see all these details. A3 plus, yeah, this is pretty tedious, but sometimes it makes it easier because I don't want to be writing out all of these later on. So I just want to sort of take care of this now so that we sort of so that we're on the same page. So let's see, 1, 2, 3, 4, 5, 6. And then we've got two more, f of h1, h2, a3, plus f of h1, h2, h3. Okay, so basically when we've expanded this, let's see here, so this is k equals 3, so we have 3 coordinates, and we have 8 terms here. And if you sort of think about how we arrived at this, it makes sense that this is 2 to the k is the number of terms we have. If you have a linear function, if you have f of a plus h, and a and h are k-dimensional vectors, then in order to split it up linearly, you end up splitting it up into 2 to the k terms. And what the terms look like is you have f of 3 things, and for each term you have each unique combination of ai's and hi's. So we've got The first term is all of them are A's, the last term is all of them are H's, and in between we have all other possible combinations. All right, so that's what happens when we expand the first term. The second term, obviously, we're subtracting f of a1, a2, a3, and then we subtract this sum. And when we write out the sum for k equals 3, there's only 3 terms. And so basically what it's going to be is, so the first one is where we have h1 and then a2 and a3 minus f of a1, h2, a3 minus f of a1, a2, h3. Okay, and if we were to go from here, then we see that we can cancel a bunch of things. We get this f, this cancels with this. Let's see here, where's the other? h1, a2, a3, these two cancel. a1, h2, a3, that's here, this cancels here. And then a1, a2, h3, so this cancels with this. Okay, so basically what we see, what has basically happened here? So basically, when we expand out f of a plus h, we get f, and the inputs of f are all the possible combinations of ai's and hj's. When we subtract f of a, we remove the term in which all of the entries are ai's. And then when we subtract this other sum, which is going to end up being what the derivative is, subtracting out this other sum removes any term f where we had only one h as an input. So one of the coordinates was an h and all the other coordinates were a's. And so all that's left here is terms where you've got 2 or more h's. So we've got like a1, h2, h3, you've got 2 h's, h1, a2, h3, you've got 2 h's, h1, h2, a3, you've got 2 h's, and then h1, h2, h3, you've got all 3 are h's. So when you do this cancellation, all that are left are the f terms where at least 2 of the coordinates are hi's. And what we eventually want is that the norm of this over the norm of h goes to 0 as h goes to 0. And all the things that survive this cancellation have at least 2 coordinates with h's in them. And if we look at part A, that's exactly what part A is telling us. It's that if you're taking a limit like this and at least 2 of the inputs are hi's, then the limit's going to be 0. All right, so now let's go ahead and write this out. This is going to be a little tricky. So let's see here. How did I write this out? Let G M N equal 1. No. This is going to be AM if n equals 0 and HM if n equals 1. And basically this is something that we're going to use to write out our proof. I don't know if this is the best way to write this out, but it's what I came up with. Oh, we got to prove linearity. To prove df A is linear, okay, so basically what we need to do is we need to look at df A of x plus lambda y. And this is basically what we use is the fact that f is multilinear is going to give us linearity. That's what this comes down to. This is going to be the sum from I equals 1 to k of f of dot, which replaces a1 through ai minus 1. And in the ith coordinate, we have xi plus lambda yi, and then all the other dots. And then we use the multilinearity of f, which means that we have linearity in the ith coordinate, and so we can break this up into f of dot xi dot plus lambda of f dot yi dot. And then we just use the linearity of finite sums to break this into the sum from I equals 1 to k of f dot xi dot plus lambda times the sum from I equals 1 to k. So just to make this clear, this is the sum of terms that look like this, but now we're breaking this up into two separate sums. So f dot yi dot, and this by definition is df a x plus lambda df a y. All right, so that's linearity. So now we get to the hard part, which is actually proving the limit. So what we need to prove that DFA is actually the derivative is we need here. Let's keep it on screen. So the limit as h goes to 0, and this is of course a vector h. It's going to be 1 over the norm of h, and what we're looking at is f of a plus h minus f of a minus this formula for the derivative that we're trying to prove. So it's the sum from I equals 1 to k of f of dot hi dot. All right, so what we need to do now is let's sort of write this out the way that we were writing things out previously. I don't know if I'm going to fit this on the same line, so I'm just going to go to the next line just in case. So now, f of a plus h, let's expand that out the way that we did with the k equals 3 case. And basically, so here's how I'm going to write this. This is going to be the sum over all vectors b in 0, 1 to the k. So b is a k-dimensional vector, each entry of which is either going to be a 1 or a 0. And in the sum is we're going to have f of g1, b1, all the way through gk, bk. Okay, so we have this, and then before we explain that, minus f of a minus the sum from I equals 1 to k of f of dot hi dot. Okay, what is the sum saying? So basically, remember how I said that when you expand f of a plus h, you get f of, and then all the terms where each coordinate of each term is either going to be ai or hi. And so you get 2 to the k terms, and you get each unique combination of ais and hi's. And that's exactly what this sum is saying. So take any vector b, so any vector of length k whose entries are zeros and ones. What f does is that for every entry which is 0, it returns, for every entry which is 0, it returns a. So if bi equals 0, then bi is 0. And then if bi is 1, then bi is hi. So it plugs in all the unique combinations of ais and hi's into this sum here. All right, so that's what it's doing. This is sort of why I wanted to introduce or do the k equals 3 explicitly, is because it would be really, if I were to just go right to this, it would be really unclear where this is coming from. But you can sort of see that you arrive at this if you expand the linearity. But remember, what we did previously is when we cancel all these things out, all that remains is all the f of whatevers where at least two of the inputs are h's. So how would we write that? So it's the limit as, so we repeat this part. Now we take the sum, and we're still taking vectors b that look like this, but here only after we do the cancellation, only a subset remains, and it's only the subset in which at least two of the entries are h. And we see here that an entry is h if b. So entry I of f is going to be hi precisely when bi equals 1. So if we need at least two of the entries to contain hi's, then we need the sum of all the bi's to be at least 2. Because remember, the number of coordinates of b, which are 1, is the number of coordinates in the inputs of f, which contain hi's instead of ai's. Okay, so it's the sum like this, and then we've got g1, b1 through gk, bk, and there we go. All right, and so this is going to be less than or equal to, basically we just use the finite, or we use the triangle inequality here, and so this is going to be less than or equal to the sum of all b in 0, 1 to the k, such that the sum of the bi's is greater than or equal to 2. We've got 1 over the norm of h. Then we've got f of g1, b1 through gk, bk. All right. And so what is, oh, I'm missing a limit. Where did that vertical line come from? And that one. Oh, norms, duh. Okay. Okay, so, what is each of these limits? Well, in this limit, we've got f of something, and at least two of the entries are hi's. And if there's additional hi's, you can just replace them. If there's 3 or more hi's in the inputs, you can take those and replace them with 0, because we're taking the limit as h, the vector, goes to 0. Actually, wait, if h is going to 0, then all the Euclidean spaces, I'm pretty sure, have to be Rn. And so that issue I was talking about in part A doesn't even matter. You can think of each EI as R to some dimension. Okay, so anyways, so each of these limits on the inside here is a special case of A. Because either there are precisely two HI's in here, either there's an HI and an HJ and everything else is an AK, and then the limit from part A directly applies and it's 0. Or, alternatively, you've got more than two HI's floating around, in which case you let two of those HI's vary and the other ones you set equal to 0. And then those become your new fixed point. Because remember, part A, all of the AI's in the input of F, that's just fixed. So it can be fixed to anything. It can be fixed to 0 if you want, that's fine. All right, so but the point is this limit here is going to be 0 by part A. And so we're taking the sum of a bunch of things, which is 0, and so it's 0. And so therefore, this derivative formula that's given above, it is linear, and it does satisfy the limit condition that derivatives need to satisfy, and so it is in fact the derivative. So yeah, that's all we need to do for this exercise, and so yeah, that's it. So it's like this formula, I don't know how you would necessarily come up with this on your own, but basically this is just a generalization of, like, we have formulas for linear and bilinear functions and their derivatives, so it's natural to take multilinear functions and ask what is their derivative, and can we use the techniques from linear and bilinear functions to determine the derivatives of multilinear functions. And in fact you can, and it ends up being a little more complicated, and you really need to think about how this cancellation all works, but I mean, you just follow these steps and you get it. And we did have to introduce some sort of interesting notation here. But as long as you sort of have, if you sort of write it out for like a small k, like k equals 3, then it should be pretty obvious how this works out. And that's sort of why a lot of times if you're struggling with something where you're trying to prove something in an n-dimensional case, it can really help to sort of write things out for like a lower dimension. Maybe like 1 or 2 here doesn't really work because we already know that, and we see there's a lot of details that are added here once you move beyond 2 dimensions. Once you move beyond bilinear, there's more details that come into play, and so you need to choose something like k equals 3 in order to really see what's happening. But once you do, it really sort of makes all this abstraction make sense. You can sort of get a better grasp on it by viewing it as an extension of the more finite dimensional stuff. But yeah, so this is sort of a tricky exercise. There's a lot of details, but this is how you do it, and I don't think this is the neatest solution, but this is all that all of this information can be used to create a solution that looks as nice as you want. And maybe there are nicer solutions out there, but this one certainly works. And so there you go, and that's it. We're done with this exercise.